Here's something that should bother you more than it probably does. Every equation in physics works equally well forward and backward in time. Take the laws of gravity, quantum mechanics, electromagnetism. Run them in reverse, and they're still valid. The physics doesn't care which direction time flows, and yet time flows in one direction, always, without exception. You remember yesterday, but not tomorrow. Eggs break, but don't unbreak. Heat moves from hot to cold, never the other way. The universe was born ordered and is becoming chaos. Why? Not how. We can describe what happens. Why? Why does time have a direction when the laws that govern it don't? This is not a philosophical question. This is one of the most serious, unsolved problems in all of physics. And the answer, when we find it, will change everything we think we know about the nature of reality. Welcome to Void Atlas. I'm your host, and today we're going somewhere genuinely strange. Not black holes, not the end of the universe, not alien civilizations, but something closer, more personal, and in some ways more disorienting than any of those. We're going after time itself. Specifically, we're going after the question of why time has a direction, why the past is different from the future, why your memories only work one way, why there's a before and an after at all, when the fundamental laws of the universe don't seem to care about the difference. This question has a name. Physicists call it the arrow of time, and it's been bothering the smartest people in physics for over 150 years. Ludwig Boltzmann spent his career on it, and it contributed to his tragic death. Richard Feynman called it our greatest mystery. Sean Carroll at Johns Hopkins has dedicated much of his career to unraveling it. Roger Penrose has proposed a radical solution that involves the structure of the Big Bang itself. And we still don't have a complete answer. So let's start from the beginning. Let's start by making sure you actually understand why this is so strange. Because I think most people, when they hear quote 3, think, obviously. Of course time only moves forward. That's what time does. What's the mystery? And the mystery is this. Science is supposed to explain why things are the way they are. Not just describe them, but explain them, derive them from deeper principles. And when you look at the deepest principles of physics, the actual equations that govern how particles and fields behave, you don't find anything that says time must move forward. The equations are symmetric. They work equally well in both directions. Let me give you a concrete example. Newton's laws of motion, the laws that govern how objects move when forces act on them, are time-symmetric. If you film a ball rolling across a frictionless surface and play the film backward, you can't tell that it's running in reverse. The backward-running film still obeys Newton's laws perfectly. The physics doesn't distinguish forward from backward. What about gravity? Einstein's general theory of relativity, our best description of gravity, is also time-symmetric. The equations that describe how mass curves space-time work the same way regardless of whether you're running time forward or backward. A planet orbiting a star looks exactly the same run backward as forward. There's no way to tell which direction time is flowing from the orbit alone. Quantum mechanics? Also time-symmetric. The Schrödinger equation, which describes how quantum states evolve, runs equally well in both directions. If you reverse the time evolution of a quantum system, you get another valid solution. Electromagnetism? Maxwell's equations are time-symmetric. There's even a famous problem in classical electromagnetism, the Wheeler-Feynman absorber theory, that explicitly uses the time-symmetric nature of Maxwell's equations to derive new predictions, some of which have been confirmed experimentally. In fact, the only known exception to time symmetry in fundamental physics is an extremely subtle violation in the behavior of certain subatomic particles called K mesons and B mesons, discovered in experiments in the 1964 and confirmed since. This violation is real but tiny, utterly insufficient to explain the overwhelming macroscopic arrow of time we observe in everyday life. So, the fundamental laws of physics are, to an excellent approximation, time-symmetric. And yet time, as we experience it, is not symmetric at all. There is a past and a future. There is a direction to the flow of time that feels absolutely fixed, absolutely non-negotiable. Something is wrong. Or rather, something is not fully explained. And that's what we're going to dig into. Let's start with the concept that is central to this whole problem: entropy. Entropy is a measure of disorder. Or more precisely, and this matters, entropy is a measure of the number of possible microscopic arrangements that correspond to a given macroscopic state. Let me unpack that, because it's the key to everything. Consider a box of gas molecules. If all the molecules are crowded into one corner of the box, there are relatively few ways to arrange them all in that corner, fewer possible microstates. If the molecules are spread out evenly throughout the box, there are an enormously larger number of ways to arrange them, many more microstates. The spread-out state corresponds to a higher entropy. The second law of thermodynamics, one of the most important laws in all of physics, says that the entropy of a closed system tends to increase over time. In everyday language, things tend to become more disordered. Gas expands to fill its container. Milk mixes into coffee and doesn't unmix. Ice melts in a warm room. Eggs break. Buildings crumble. And this, physicists will tell you, is the arrow of time. The direction from low entropy to high entropy is the direction of time. The past is low entropy. The future is high entropy. The arrow of time is the arrow of increasing entropy. But here's where it gets subtle, and where the real mystery emerges. Why does the second law of thermodynamics hold? Why does entropy increase? The statistical mechanics answer, developed primarily by Ludwig Boltzmann in the 1870s and 1880s, is that high entropy states are simply overwhelmingly more probable than low entropy states. If you start with a system in a specific, orderly, low entropy configuration and let it evolve randomly, it will almost certainly evolve toward one of the vastly more numerous high entropy configurations. The system spreads out through the available configuration space, and there's so much more high entropy configuration space than low entropy configuration space that it almost always ends up in a high entropy state. This is a probabilistic argument. Entropy increases not because there's a law that says it must, but because high entropy states are astronomically more probable than low entropy states. There's nothing in the microscopic laws of physics that prevents entropy from decreasing. It's just extraordinarily unlikely. If you waited long enough, you'd eventually see entropy spontaneously decrease in some small system. These are called fluctuations, and they're real and observable at small scales. But at the scale of everyday objects, the probability of a significant spontaneous decrease in entropy is so tiny it might as well be zero. So far, so good. But now, here's the problem that Boltzmann himself wrestled with. The statistical argument I just gave you is time-symmetric. If the laws of physics are time-symmetric, and if the reason entropy increases is statistical probability, then by exactly the same argument, entropy should have been increasing toward the past as well as toward the future. In other words, the statistical argument predicts not just that entropy will be higher in the future, but also that entropy was higher in the past. If the current state of the universe is very specific and ordered, then the most probable history is that it arose from a more disordered past. A past where things were more random, less structured. You'd expect entropy to be high both in your past and your future, with a minimum right now. But that's not what we observe. We observe a universe with a clear past-future asymmetry. The past has lower entropy than the present. Stars were younger in the past. Structures were less complex. The universe had less disorder. As we go further and further back to the Big Bang itself, the universe was in an extraordinarily low entropy state. Why? Why was the early universe in such a remarkably low entropy state? Nobody forced it to be. There's nothing in the laws of physics that required the Big Bang to be ordered rather than disordered. And yet the Big Bang appears to have been one of the most low-entropy events in the history of the universe. Extraordinarily, improbably ordered. This puzzle is sometimes called the past hypothesis, a term coined by philosopher of physics David Albert. The past hypothesis is simply the assumption that the early universe had extremely low entropy. It's an assumption, not a derived result. We assume it because the evidence, the fact that we observe an arrow of time, the fact that the universe looks different in its past than in its future, demands it. But we can't yet derive it from more fundamental principles. And this is the real depth of the arrow of time problem. It's not just, why does entropy increase? Boltzmann gave us a good statistical answer to that. The real question is, why did the universe start in such a low entropy state? Why was the Big Bang so ordered? And does the fundamental time symmetry of physics mean that the arrow of time is, in some deep sense, an illusion? A feature of our position in a larger time-symmetric universe rather than a fundamental asymmetry in the laws of nature? Let me tell you about Boltzmann's own struggle with this, because the history is tragic and illuminating. Boltzmann was one of the great physicists of the 19th century. He developed statistical mechanics, the framework that explains thermodynamics in terms of the microscopic behavior of atoms and molecules. He proved, mathematically, that the entropy of a gas would tend to increase over time, the result known as the H theorem. It was a landmark achievement. But critics immediately spotted the problem. Boltzmann's proof relied on the laws of mechanics, which are time-symmetric. How could a time-symmetric set of laws produce a result that depended on the direction of time. This was pointed out by Joseph Loschmidt in a famous objection now called Loschmidt's paradox. If you reverse all the velocities of all the molecules in a gas, the system is allowed by the laws of physics to evolve backward. Entropy should decrease. Boltzmann's H theorem should be violated. Boltzmann struggled with this for years. His eventual response was the statistical argument I described earlier. Entropy increases toward the future because high entropy states are simply more probable. But this doesn't escape Loschmidt's paradox completely. It just shifts the question. Why was the initial state of the system low entropy in the first place? Late in his life, Boltzmann proposed something radical, an idea now called the Boltzmann brain hypothesis, which we've discussed in a previous video. The idea was that perhaps the entire universe, everything we observe, is a massive statistical fluctuation. The universe happened to fluctuate into a low entropy state, and the arrow of time we observe is just the system returning to equilibrium from that fluctuation. This idea has a fatal problem. If our entire observable universe is a fluctuation from a high entropy background, then the most probable fluctuation that could give rise to us, to observers who perceive a low entropy past, would be an extremely tiny fluctuation, just big enough to produce our memories and our immediate environment, not actually the entire vast universe we observe. The most likely version of a fluctuation-produced universe would be a single brain spontaneously fluctuating into existence, with all the memories and perceptions of a larger universe, without that larger universe actually existing. This is the Boltzmann brain problem. And it's not just a curiosity. It's a serious reductio ad absurdum of the idea that the arrow of time is due to a statistical fluctuation from an equilibrium state. Boltzmann died in September 1906 by suicide during a period of depression. The debates about his ideas, which were not fully accepted by the physics community during his lifetime, had taken a serious toll. He is now recognized as one of the founders of statistical mechanics and thermodynamics, and his grave in Vienna bears the equation S equals K log W, the formula relating entropy to the number of microstates, which encapsulates his great contribution. The problem he was wrestling with, why the universe started in a low entropy state, remains unsolved today. Let me now take you through the modern approaches to this problem. Because there are several serious proposals, each with interesting implications. The first approach, associated most prominently with Sean Carroll and Jennifer Chen, argues that the arrow of time is a consequence of the cosmological structure of the universe, specifically of the fact that the universe is very young and very far from equilibrium. In this view, the universe didn't start in a specially chosen low-entropy state. Rather, the multiverse, the collection of all possible universes, is in a state of high entropy overall, but it naturally produces local regions with temporarily low entropy. Our Big Bang was one such region. It was born from quantum fluctuations in some larger parent space, and it happened to start in a low entropy configuration by chance. Though in the context of an infinite multiverse, even extraordinarily rare events happen. Carroll argues that the arrow of time points away from the Big Bang in both directions. In our region of the universe, we experience time as moving forward, away from the Big Bang. But there might be other regions born from the same parent space where the arrow of time points in the opposite direction, where forward for them is what we would call the past. These regions are causally disconnected from us. We could never observe them, but they're there. And the multiverse as a whole has no preferred arrow of time. This is a provocative idea, and it has the virtue of connecting the arrow of time to cosmology in a deep way. But it relies on the multiverse, a structure that is currently unverifiable, and many physicists are skeptical. The second approach, associated with Roger Penrose, goes in a completely different direction. Penrose argues that the arrow of time is not statistical but fundamental, that it's baked into the structure of quantum mechanics at the deepest level, in a way we don't yet understand. Specifically, Penrose points to the measurement problem in quantum mechanics. When we measure a quantum system, when we observe which of several possible states it's in, the wave function collapses. It goes from a superposition of possibilities to a single definite state. And this collapse is time irreversible. It's one of the few processes in all of physics that has a built-in direction. Before measurement, superposition. After measurement, definite state. The collapse doesn't run backward. Penrose argues that this collapse is not just a feature of observation in the ordinary sense. He proposes that it's a fundamental physical process, one that he calls objective reduction, or OR, and that it's responsible for the arrow of time. In his view, the quantum gravity effects that mediate wave function collapse are intrinsically time asymmetric, and this is where the direction of time ultimately comes from. Penrose's proposal is speculative and controversial. It requires physics beyond the standard model, specifically a theory of quantum gravity that doesn't yet exist. But it's a serious attempt by one of the most creative physicists alive to solve the arrow of time problem at the deepest level. A third approach looks at the CPT theorem. This is a fundamental result in quantum field theory, proved in the 1950s, which states that all physical laws must be symmetric under the simultaneous reversal of three things: charge, switching particles with antiparticles; parity, reflecting space as in a mirror image; and time, reversing the direction of time. This is called CPT symmetry. The theorem says that if you reverse all three simultaneously, the physics looks the same. But it doesn't say that each one individually is symmetric. And we know that CP symmetry, the combination of charge and parity reversal, is violated in certain particle interactions. This is the source of the subtle time reversal violation I mentioned earlier, in K mesons and B mesons. Because CPT must hold, if CP is violated, then T must be violated to compensate. So time reversal is violated at the level of fundamental particle physics. But only slightly. This violation is far too small to explain the macroscopic arrow of time. We can't get from the tiny T violation in meson decays to the reason why broken eggs don't unbreak. The scales are completely mismatched. But this raises an interesting philosophical question. Is the arrow of time we experience a macroscopic statistical phenomenon layered on top of a fundamentally time-symmetric universe? Or is there a genuine fundamental time asymmetry at the level of basic physics that we've only partially discovered? we don't know. Before I go further, and there's a lot more to cover, I want to pause and make sure you're still with me, because this topic is genuinely one of the most conceptually challenging things physics deals with. If you're someone who finds this kind of deep questioning about the nature of reality at its most fundamental level compelling enough to come back for more, subscribe to Void Atlas. Every week, we take a question that doesn't have a clean answer, and we follow it as far as we can. That's what we're doing right now, and I'm grateful you're here for it. Let me take you now into the most recent developments. Because in the last decade or so, there's been a revolution in how physicists think about time, driven partly by new work in quantum gravity, partly by new work in quantum information theory, and partly by some genuinely surprising experimental results. The first development concerns quantum entanglement and its relationship to time. This is recent cutting-edge research, and it's genuinely strange. In quantum mechanics, two particles can be entangled, meaning their quantum states are correlated in a way that persists regardless of distance. Einstein famously called this spooky action at a distance. When you measure one entangled particle, the other one instantly knows about the measurement, regardless of how far apart they are. Now, recent theoretical work and some tentative experimental evidence suggests that entanglement might be deeply connected to the emergence of time itself. In a framework called thermal time, developed by Carlo Rovelli and Elaine Cohn, time emerges from the thermal properties of quantum states. In a universe with no preferred time direction, different observers experience different times depending on their relationship to the quantum information structure of their environment. Time, in this view, is not a background parameter. It's an emergent property of quantum information. This is connected to work on the so-called quote 10, the idea that the apparent flow of time emerges from the structure of quantum entanglement and the growth of correlations between systems. When a quantum system evolves and becomes increasingly entangled with its environment, this entanglement growth is irreversible, and this irreversibility is what we experience as the arrow of time. In 2023, researchers published work suggesting that the growth of quantum entanglement in a system can be directly measured and shown to be the physical mechanism behind the increase in entropy. The arrow of time in this picture is the direction in which quantum entanglement grows. And it grows in one direction because, and here we come back to the same fundamental question, the universe started in an extremely low entanglement, low entropy state. A second recent development involves the holographic principle and black holes. We've discussed the holographic principle in previous videos. The idea that all the information in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region. Recent work by Juan Maldacena and others has suggested that the flow of time is intimately connected to the holographic encoding of information. Specifically, there's a relationship called the ER equals EPR conjecture, which Maldacena proposed with Leonard Susskind in 2013, between quantum entanglement and space-time geometry. Entangled particles in this framework are connected by microscopic wormholes, and the growth of entanglement corresponds to the growth of space-time structure. The emergence of time in this picture is tied directly to the emergence of space, Both arise from the quantum information structure of the fundamental degrees of freedom. If this is right, it means that time and space are not fundamental. They're emergent. They arise from something more basic, quantum information. And the arrow of time is not a fundamental feature of physics, but an emergent feature that arises because the universe started in a particular quantum informational state. This is a dramatic conclusion. It means that the question, why does time flow forward, might ultimately be answered by, because the universe began in a particular quantum state, and the growth of entanglement from that state defines what forward means. But it doesn't answer why the universe began in that state. That question, the past hypothesis, remains at the bottom of everything. Let me now talk about something that I think is underappreciated in popular discussions of the arrow of time: the role of memory and causality. The reason we experience time as flowing forward is not just about entropy in the physical sense. It's also about memory, about the fact that we retain information about the past, but not the future. And the reason we retain information about the past is that creating a record of something, a memory, a photograph, a footprint in sand, requires an interaction that increases entropy in the surroundings. The record-creating process is irreversible. You can't easily unremember something, just as you can't easily unbreak an egg. This connection between memory and entropy is profound. Our sense of time's arrow, the psychological experience of time flowing from past to future, is intimately connected to the thermodynamic arrow. We remember the past because making memories increases entropy. We can influence the future, but not the past, because causality flows in the direction of increasing entropy. David Deutsch, the physicist who pioneered the theory of quantum computation, has argued that the arrow of time is closely connected to the concept of causality. Causality, the principle that causes precede effects, is what gives time its direction in our experience. And causality, he argues, is grounded in the same thermodynamic asymmetry that Boltzmann identified. The universe is not symmetric between cause and effect, just as it's not symmetric between the past and the future. And the reason is the same in both cases: the low entropy of the past. There's also a deep connection between time and the concept of information itself. When a physical system records information, when it forms a, quote, 13 of some past state, the recording process is irreversible in exactly the way that entropy increase is irreversible. Landauer's principle, proved by Rolf Landauer in 1961, says that erasing one bit of information necessarily releases a minimum amount of heat, an amount equal to K times T times the natural log of 2, where K is Boltzmann's constant and T is temperature. Information erasure increases entropy. The connection between information and thermodynamics runs deep. And this connects to a beautiful way of restating the arrow of time problem. The universe, in its early low-entropy state, contained a lot of unrealized information, a lot of potential for correlations, for structure, for complexity. As the universe has evolved, it has been actualizing that potential. Structures have formed, information has been processed, memories have been created, entropy has increased. The flow of time in this picture is the universe computing. The arrow of time is the direction of computation. This is not just a metaphor. Physicists like Seth Lloyd at MIT have developed precise quantitative frameworks for understanding the universe as a quantum computer, where the quote underscore 1 4 underscore the evolution of quantum information drives the thermodynamic changes that constitute the arrow of time. Now let me ask the question that I think is the most important one, and also the most disturbing. Is the arrow of time real, or is it an illusion? This sounds like a strange question. Time clearly flows forward. You feel it. The past is different from the future. What could it possibly mean for the arrow of time to be an illusion? Here's the argument for the illusion view. The fundamental laws of physics are time-symmetric. The direction of time that we experience arises not from the laws themselves, but from the boundary conditions, from the particular initial state the universe happened to be in at the Big Bang. If the universe had started in a different initial state, or if there's a region of the universe where the initial conditions were different, the arrow of time there might point in the other direction. Quote 1 5 is not fundamental. It's a contingent fact about our particular location in cosmic history. From the perspective of the fundamental laws, there's no quote 1 6 there's no flowing present. The universe at the deepest level might be a four-dimensional space-time block, a fixed structure in which past, present, and future all exist equally. This is the block universe view, associated with the special theory of relativity and with philosophers like Hugh Price and David Albert. In the block universe, time doesn't flow. It just is. The apparent flow of time is a feature of how we experience the universe from within it, a feature that arises from our particular relationship to the thermodynamic arrow, from the way our brains process information, from the fact that we are entropy-increasing systems with memories. The physicist Carlo Rovelli has argued for a related but distinct view, that time is not fundamental but relational. Time exists as a relationship between physical systems. There is no single universal time. Different systems have different times, and the flow of time is an emergent feature of the thermodynamic and informational structure of the systems involved. The physicist Lee Smolin, by contrast, has argued the opposite, that time is fundamental, that the block universe view is wrong, and that the present moment is genuinely real in a way that the laws of physics don't currently capture. In his view, the laws of physics themselves evolve in time. They are not fixed, eternal truths, but aspects of a universe that is genuinely changing, genuinely temporal. These views are not just philosophical preferences. They have different implications for how we interpret quantum mechanics, for what we expect from a theory of quantum gravity, and for what we should look for in experiments. The nature of time is not just a metaphysical question, it's a scientific one. And the answers we find will matter. If time is not fundamental, if it's emergent from quantum information, then understanding the origin of the arrow of time is the same as understanding how the universe's quantum information structure gives rise to the space-time we inhabit. If time is fundamental, if the present moment is real in a way physics doesn't yet capture, then we need new physics. Physics that goes beyond the block universe and includes genuine temporal evolution. Either way, we need to do better. Let me bring this back to something personal. Something that I think we don't talk about enough when we discuss the arrow of time. Your memories only go one way. You remember yesterday, but not tomorrow. You know your past, but not your future. This asymmetry, this fundamental asymmetry in how you relate to the two directions of time, is something we take completely for granted. It feels obvious. Of course you remember the past. Of course you don't remember the future. But given what we know about physics, it's not obvious at all. The fact that memories only point one way is a consequence of the same thermodynamic arrow we've been discussing. Your brain is an entropy-increasing system. It records information about events that have happened, low-entropy records of past states. It cannot record information about events that haven't happened yet, because those events don't exist yet in a form that can be recorded. The arrow of causality, the fact that causes precede effects, runs in the same direction as the thermodynamic arrow. And all of this traces back to the fact that the universe started in a low-entropy state 13.8 billion years ago. Your memories, your sense of having a past, your experience of time flowing, are a direct consequence of the Big Bang, of the particular way the universe began, of a boundary condition that we don't yet fully understand. This is not a comfortable thought. It means that the most intimate, most personal aspect of your experience, your sense of being embedded in time, of moving through it, of having a history, is grounded in a fact about the distant cosmic past, a fact that you didn't choose, a fact that physics can describe but not yet fully explain. The arrow of time is personal. It's yours. And it's a mystery. This is Void Atlas. I'm your host, and this particular question, the arrow of time, is one I find more personally unsettling than almost anything else in physics. Because it reaches into the most fundamental aspects of experience, into what it means to remember, into what it means to exist in a world where there's a past and a future, into the question of whether that distinction is real or is itself an emergent feature of our position in a larger, possibly time-symmetric reality. We don't have a complete answer. Boltzmann didn't have it. Feynman didn't have it. Carroll and Penrose are still working on it. The question is open, and it matters more than almost any other question in physics. Subscribe to Void Atlas. Come back next week. We'll keep following the physics wherever it leads, even when it leads somewhere as strange and as personal as the nature of time itself. I'm your host. Thank you for spending this time with me. And remember, the fact that you remember this and not what comes next is itself a profound clue about the universe we inhabit. Until next time, whenever that is. But I'm not done yet, because there are dimensions of the arrow of time problem I haven't addressed. and some of them are the most surprising. Let me tell you about what happens to the arrow of time inside a black hole. We've established that the thermodynamic arrow of time, the direction in which entropy increases, defines the direction of time for us in the observable universe. But what about inside a black hole? What does time look like there? Inside the event horizon of a black hole, something extraordinarily strange happens to the structure of space-time. The radial direction, the direction pointing toward the singularity, takes on the character of time. You can only move toward the singularity, just as in normal space-time, you can only move toward the future. The singularity is your future, regardless of what direction you try to move in. This means that inside a black hole, the arrow of time points toward the singularity, not outward. There's no __quote _18__ inside the event horizon, in the same way there's no past outside of it. The geometry of space-time inside a black hole enforces an arrow of time through purely geometric means, not through entropy, but through the structure of curved space-time itself. This raises a fascinating question. Are the thermodynamic and geometric arrows of time the same thing? Are they two descriptions of the same underlying reality? Or are they genuinely different phenomena that happen to point in the same direction in our experience? Stephen Hawking argued in his book, A Brief History of Time, that the arrows of time are indeed connected. He proposed 3 arrows: the thermodynamic arrow, entropy increasing; the psychological arrow, the direction in which we perceive time to flow, grounded in memory; and the cosmological arrow, the direction in which the universe expands. Hawking argued that all 3 must point in the same direction, and that the cosmological expansion is what drives the thermodynamic increase in entropy, which in turn determines the psychological arrow. This reasoning has been contested. Many physicists believe that the connection between the cosmological expansion and the thermodynamic arrow is not as direct as Hawking suggested. The universe could, in principle, continue to have a thermodynamic arrow even if it stopped expanding, as long as it remained far from thermodynamic equilibrium. But the question remains profound. The universe is expanding. The universe has an arrow of time. Are these connected? And if so, how? There's a related question that Penrose has written extensively about. If the universe eventually reaches maximum entropy, heat death, and then what? Some cosmological models, including Penrose's conformal cyclic cosmology, propose that a universe at maximum entropy can somehow give rise to a new Big Bang. In Penrose's model, the universe cycles through eons, each eon beginning with a Big Bang equivalent and ending with heat death. The transition between eons is mediated by conformal rescaling of the metric, and the low entropy initial condition of each new eon is inherited from the properties of the previous eon's heat death. This is speculative, but it's serious speculation by one of the most mathematically sophisticated physicists alive. And if something like Penrose's model is correct, then the arrow of time is ultimately cyclical. Each eon has an arrow pointing from its Big Bang to its heat death, and then a new eon begins with a new arrow. Let me take you to one more place that I think is important: the quantum measurement problem and its relationship to time. I mentioned earlier that wave function collapse in quantum mechanics is time irreversible, that measurement produces a definite state from a superposition, and this process doesn't run backward. But I didn't address the deepest question: what causes collapse? What constitutes a measurement? And why is collapse irreversible? The standard Copenhagen interpretation of quantum mechanics simply says that collapse happens when a measurement is made, without specifying what a measurement is or how collapse occurs. This is unsatisfying, and it's at the root of the measurement problem. One approach, the many worlds interpretation, developed by Hugh Everett III in 1957, denies that collapse happens at all. Instead, every quantum measurement causes the universe to branch into multiple branches, one for each possible outcome. All outcomes occur, we simply find ourselves in one branch. In this view, the universe as a whole evolves according to the time-symmetric Schrödinger equation, and there's no irreversible collapse. The apparent arrow of time arises from the branching structure of the many worlds wave function, combined with the low entropy initial conditions. The many worlds interpretation is controversial, but has gained significant support among physicists in recent years. One of its attractive features is that it's completely time-symmetric at the fundamental level. There's no collapse, no irreversibility built in. The arrow of time arises entirely from initial conditions, just as in Boltzmann's statistical mechanics. Another approach, the objective collapse theories, including the Girardi-Rimini-Weber theory and Penrose's objective reduction, does posit a real physical collapse process. In these theories, collapse is a genuine physical event that introduces irreversibility into quantum mechanics. The arrow of time has a quantum mechanical component as well as a thermodynamic one. Each of these approaches to the measurement problem gives a different answer to the question of where the arrow of time comes from. And the right answer to the measurement problem, which remains unknown, will likely tell us something important about the nature of time. There's one more strand I want to pull on: the connection between the arrow of time and the origin of life and consciousness. Life is a remarkably low-entropy phenomenon. A living organism maintains itself far from thermodynamic equilibrium. It takes in low-entropy material, food, sunlight, and expels high-entropy waste, using the entropy differential to maintain its complex, ordered structure. Life surfs on the thermodynamic arrow of time. It exists because of the entropy gradient between the low-entropy sun and the high-entropy cold of space. It processes information, forms memories, and makes decisions that influence its future, all in the direction of the thermodynamic arrow. Consciousness, if it arises from physical processes, is even more remarkable. It represents a level of information processing, modeling, and memory formation that seems to require a very particular relationship to the arrow of time. A conscious mind represents the past through memory, models the present through perception, and projects the future through prediction and planning. This temporal structure is only possible because the arrow of time exists, because the past is fixed and the future is open. if the arrow of time were reversed, if entropy were decreasing rather than increasing, memory and consciousness would work completely differently, or might not work at all. We exist as conscious beings because the universe has an arrow of time. And the universe has an arrow of time, at least in our region of it, because it started in an extraordinarily low entropy state nearly 14 billion years ago. This chain of connections, from the Big Bang to entropy to consciousness, is one of the most remarkable in all of science. We are products of a cosmic accident, in a sense, the accident of the universe beginning in a low entropy state. If it hadn't, we wouldn't be here to ask why. Let me try to pull everything together. We've covered an enormous amount of ground, and I want to make sure the main threads are clear. The arrow of time. The fact that time flows in one direction is not directly explained by the fundamental laws of physics. Those laws are time-symmetric. The arrow of time emerges from the initial conditions of the universe, specifically from the extraordinarily low entropy of the Big Bang. Why was the Big Bang low entropy? This is the fundamental, unresolved question, the past hypothesis. Serious proposals for answering it include multiverse models, in which the Big Bang was a fluctuation in a larger system; Penrose's conformal cyclic cosmology, in which the universe cycles through eons; quantum gravity models, in which the low entropy initial condition emerges from fundamental physics; and emergent models, in which time and entropy both arise from quantum information structure. The experience of time flowing, the psychological arrow, is grounded in the thermodynamic arrow, which is grounded in memory and causality, which are grounded in the thermodynamic asymmetry between past and future. Inside black holes, the geometric structure of space-time enforces an arrow of time independent of thermodynamics. Quantum mechanics has a potential additional source of time asymmetry in the measurement process, though its role is contested. Recent work connecting quantum entanglement, the holographic principle, and the emergence of space-time geometry suggests that time may be emergent from quantum information, a feature of the way the universe processes information rather than a fundamental property of reality. And at the bottom of all of it, the past hypothesis. Why did the universe start in such an improbably ordered state? The answer, when we find it, will likely be one of the most important discoveries in the history of physics. We are living beings who experience time. We form memories, make decisions, age, and eventually die, all in the forward direction of the arrow of time. This experience, which feels so immediate and obvious, is grounded in cosmic history, in the Big Bang, in the statistical mechanics Boltzmann developed in the 19th century, in the quantum information structure that physicists are only beginning to understand in the 21st. We are temporal beings in a universe whose temporality is not fully explained. And that should bother us. It should drive us. It should make us want to understand it. Because when we do understand it, when we finally crack the arrow of time, we will understand something about ourselves, about why we have pasts, about why we can remember but not foresee, about why we are what we are, creatures of time, embedded in a universe that flows in one direction for reasons we're still piecing together. This has been Void Atlas. I'm your host. The arrow of time is pointing forward. That means there are more videos coming, more questions, more mysteries, more corners of physics and cosmology that we haven't explored yet. And I'll be here, following the physics wherever it goes. Subscribe to Void Atlas. Come back next week. The universe has more to show us, and time, despite all the uncertainty about its nature, keeps moving in exactly one direction, forward. Until next time, I'll see you there. Actually, I want to go one more place, because there's a thought experiment that I think captures the strangeness of the arrow of time better than any abstract argument. And it involves something you do every single day: watching a video. When you watch a video, any video, including this one, you're watching something that was recorded in the past and is being played back in the present. The recording process captured a specific sequence of events in a specific order. The playback process reproduces that sequence in the same order. Now imagine watching a video in reverse. You'd immediately know it was playing backward. Why? Because certain things would happen that never happen in nature. Water would flow upward, back into a tipped glass. Flames would pull smoke and combustion products back together into unburned wood. Broken objects would spontaneously reassemble from their shattered pieces. People would walk backward into rooms, exit through doors, and so on. All of these backward events violate our intuitions because they violate the thermodynamic arrow of time. They involve entropy decreasing. And entropy decreasing, while not forbidden by fundamental physics, is extraordinarily improbable. So improbable that we never observe it at the macroscopic scale. But here's the thing. At the microscopic level, individual particle collisions look the same forward and backward. If you filmed a single proton bouncing off another proton and played the film backward, you could not tell which way it was running. The microscopic collision is time-symmetric. The macroscopic irreversibility emerges from the statistics of huge numbers of particles, not from any individual particle's behavior, but from the collective behavior of billions upon billions of them. This is one of the most beautiful and profound things in all of physics. Macroscopic irreversibility, the arrow of time, is an emergent phenomenon. It arises from the collective behavior of systems with many degrees of freedom, not from any fundamental time asymmetry in the laws governing individual particles. And yet it's so robust, so overwhelming, so universal at the macroscopic scale, that it defines our entire experience of reality. The asymmetry that doesn't exist at the level of individual particles is completely dominant at the level of eggs and glasses and human beings and stars. This is emergence at its most dramatic. The universe at the level of fundamental particles is essentially timeless, time-symmetric, reversible, without a preferred direction. The universe at the level we experience it is deeply temporal, irreversible, directional, flowing always in the same direction. And the transition between these two descriptions involves one of the deepest unsolved problems in physics. Let me also tell you about something called the Loschmidt paradox in a different light. because it's not just a historical curiosity. It's a genuinely unresolved tension in the foundations of physics. Boltzmann derived his H theorem, proving that entropy increases, from the microscopic laws of mechanics. But those laws are time-symmetric. How can you derive a time-asymmetric result from time-symmetric laws? The answer, as Boltzmann eventually realized, is that you can't, unless you smuggle in an additional assumption. The assumption Boltzmann used, which he called the Stoßzahlansatz, or molecular chaos assumption, states that the velocities of colliding particles are uncorrelated before their collision. This assumption is reasonable for a gas that's not in a specially prepared state. But the key word is "23". The assumption treats "24" and "25" differently. It assumes that particles are uncorrelated before they collide, not after. And this breaks the time symmetry. The molecular chaos assumption is itself a statement about the arrow of time. It says, the world we're starting from is one in which correlations haven't built up yet, where the gas is in a ___26__ disordered state. This is a statement about initial conditions, about the past hypothesis again. The H theorem doesn't derive the arrow of time from the fundamental laws. It derives the increase of entropy from the fundamental laws plus an assumption about initial conditions that already encodes the arrow of time. This is circular in a sense. We assumed the arrow of time to derive the arrow of time. But it's not viciously circular. It's telling us something important. The arrow of time is consistent with time-symmetric fundamental laws given the right initial conditions. The mystery is not that the laws allow an arrow of time. The mystery is why the initial conditions are the way they are. This brings me to what I think is the most important unsolved question in this whole area. Could we ever derive the past hypothesis from something? Could we ever explain, rather than merely assume, why the universe started in a low entropy state? This would require understanding the quantum state of the universe at the very beginning. It would require a theory of quantum cosmology, a quantum mechanical description of the universe as a whole, including its initial state. This is one of the holy grails of theoretical physics. Several approaches exist. The no-boundary proposal of Stephen Hawking and James Hartle, developed in the 1980s, tries to calculate the quantum state of the universe by summing over all possible compact geometries, treating the origin of the universe as a quantum event with no definite boundary in time, analogous to the way the South Pole has no boundary below it on Earth. This proposal naturally selects for a low entropy initial state in some formulations, which is encouraging. But the calculations are technically extremely difficult, and different implementations give different answers. Another approach, associated with Alexander Vilenkin, posits that the universe originated through quantum tunneling from literally nothing, from a state with no space, no time, no matter. The quantum tunneling process would naturally produce a universe in a low entropy state in this picture. But nothing is a philosophically tricky concept, and the derivation is controversial. A third approach uses the ideas of loop quantum cosmology, a quantum gravity framework developed by Abe Ashtekar, Martin Bojewald, and others, in which the Big Bang singularity is replaced by a big bounce. In this picture, the universe didn't begin at the Big Bang. It contracted from a previous phase, bounced, and began expanding. The low entropy initial condition of our current expansion might be a consequence of the dynamics of the bounce, a question that is actively being researched. None of these approaches has definitively succeeded. We don't have a theory of quantum cosmology that unambiguously predicts the low entropy initial state of the universe. The past hypothesis remains an assumption, but it's an assumption that is being actively worked on by some of the best minds in theoretical physics, using some of the most sophisticated mathematics ever developed. And the fact that it's being worked on, that people are seriously trying to derive the arrow of time from first principles, is itself a remarkable thing. We live in an era when questions that would once have been considered purely philosophical, questions about why time flows, about the nature of the present, about the relationship between the microscopic and macroscopic descriptions of reality, are being addressed by physicists with real, quantitative, testable ideas. Not all of these ideas will be right. Most of them will probably turn out to be wrong in various ways. But the enterprise, the attempt to understand the deepest features of physical reality from the ground up, is one of the most extraordinary intellectual endeavors in human history. The arrow of time is one of the hardest targets in that enterprise. It requires understanding thermodynamics, quantum mechanics, gravity, cosmology, and possibly consciousness all at once. Because all of these things are connected to the question of why there's a difference between past and future. It requires the kind of synthesis across disparate fields that rarely happens, and when it does, tends to produce the most significant advances in science. We don't have that synthesis yet, but we're closer than we were, and the framework is becoming clearer. The question is increasingly well posed, the constraints are increasingly tight, the approaches are increasingly sophisticated. The answer is out there. We just have to keep following the physics. This is Void Atlas. I'm your host, and today we've gone as deep as I know how to go into the question of why time flows the way it does. From Boltzmann and his tragically unresolved paradoxes to the modern work on quantum entanglement and emergent spacetime, to the open question of the past hypothesis and what quantum cosmology might one day tell us about why the universe started the way it did. The arrow of time points forward, always, for reasons that are partly understood and partly mysterious. And in that mystery, in the gap between what we know and what we don't, lies some of the most important unsolved physics of our time. Subscribe to Void Atlas. Every week, a new question worth asking. Every week, a journey to the edge of what's known. I'm your host. Thank you for being here. The arrow of time continues to point forward, and wherever it's pointing, that's where we're going. See you there. One last thing, and I promise this is the last, because it's the most personal. Think about what you're doing right now. You're watching a video. You're taking in information. You're forming a memory, or maybe several memories, about what you've learned today, about entropy, about Boltzmann, about the past hypothesis, about the question of why time has the direction it does. Those memories are forming right now, not because your brain has any special power to record the past, but because your brain is an information processing system, and information processing systems in a universe with a thermodynamic arrow of time naturally form records of their past states. Your memories are a consequence of entropy, of the arrow of time, of the Big Bang. The knowledge you're acquiring right now about the deepest mystery in physics is itself an instance of that mystery. You are a system in which information is accumulating, entropy is increasing, and the arrow of time is being written, moment by moment, into the physical state of your brain. You are the arrow of time, made conscious. And you're asking, from inside it, why it exists. That question, asked by a being made of atoms, in a universe made of physics, about the direction of the flow of time that makes asking and answering questions possible, might be the most extraordinary question anyone has ever asked. We don't have the full answer yet, but we're asking the right question. And in science, that's everything. This is Void Atlas. I'm your host. Until next time.